Okay, we're talking about redox reactions, and a redox reaction is notable because electrons are transferred between the reactants. So not only do you have atoms switching around, but you also have charges switching around. Wake him up, please. All right. Now, another thing that you need to know is re and dox must occur in pairs. So it must be paired. You can't have a re without an ox, because if you lose some electrons, somebody must find them. All right, your memory hook for this entire procedure is Leo the lion says grr. And I think if you went to a PhD in chemistry and said Leo the lion says grr, he would say, oh, redox, got it. Everybody uses this. The loss of electrons is oxidation. The loss of electrons is oxidation. Okay, this is kind of counterintuitive, so I always remember that across the arrow, the oxidation number will increase. And whatever is oxidized becomes the reducing agent. So you're going to think the opposite agent. I guarantee you will be asked to identify the reducing agent, the oxidizing agent, and you need to be fluent in this. The gain of electrons is reduction. The gain of electrons is reduction. So, across the arrow, the oxidation number decreases. And whatever is reduced becomes the opposite agent, so it is the oxidizing agent. All right, now, this has to be in pairs, because whoever loses electrons, there must be something around to gain them. They just can't go flitting off into space. This is a I'll give you and you'll take from me kind of thing. Okay. So, if you shrinky-dinked yourself down into an equation and looked at an equation, there aren't really oxidation numbers, or here's the synonym, an oxidation state for every atom. This is a bookkeeping thing that we have done so we can balance these equations. You're going to have to assign an oxidation number or an oxidation state for every atom in an equation. Here are the rules to do so. Atoms in their elemental form have an oxidation number of 0. That means if you find them on the periodic table, their oxidation number is 0. And I'm even talking about the diatomics. The oxidation number of any of the diatomics, you will write them properly. There are 2 of them, but the oxidation number is 0. Monoatomic ions have an oxidation number equal to their charge. Well, who gets that? Nobody. If you had this compound, okay, 1 atom ion, its charge would be exactly what it needed to balance the chlorine. So this would be +1 and this would be -1. Nonmetals have negative oxidation numbers. Oxygen is -2 in all compounds with the exception of peroxides in which it is -1. This is the only peroxide you are going to have to worry about, and this is the only time where the oxidation number of oxygen is -1. Any other time, it's going to be -2. If you find hydrogen with a nonmetal, hydrogen will have an oxidation number of +1. If you find hydrogen with a metal, hydrogen will have an oxidation number of -1. the sum of all oxidation numbers in any neutral atom, I'm sorry, this should be compound, in any neutral compound is 0. Here is a neutral compound. If you took the oxidation numbers and added them up, it would equal 0. Likewise, if you had a polyatomic ion that has a charge, this is telling you that when you add up the oxidation numbers, it would equal -2. So far, so good? Okay. Now, I would like you to assign oxidation numbers to all of these atoms in A, B, and C. I will wait here.